Hello, welcome. My name is John Ibini Ode, and today we are going to be performing binary analysis, capture the flag of a Linux executable file. All right, so I have it here in this directory as payload. So we are going to know the functionality of this file here, what the file does or what this program does, and the input this program wants from us. All right, so first of all, in your binary analysis, the first tool you need to use is the file command here, which tells you the type of this payload, that is the type of this file here. So I'm going to use file on this, and we see that this is an ASCII test. Now, is this truly an ASCII test? So let's find out. So I'm going to display the file. Let's display the first 10 lines. All right, so this looks like an ASCII file because it contains alphabet and numbers. All right, but there is something to look out for here. We have the plus symbol here, which is common in base 64 encoded files. So since I have made this assumption, let's see if this is a base 64 encoded file by decoding it. So I'm going to use base 64 decode, and I'm going to call this let's name this decoded payload file. All right, so we have it as decoded payload file. Let's see the file type again. All right, so we now see that this is a gzipped compressed data, which means there are other files or data hiding inside this file here. You know, when we use the file command on this payload here, we got it as what? An ASCII test. Then when we decoded it, we got what? Decoded PL file. And now we are trying to check the content of this file, and we now discover that this is what? A gzip compressed data. Alright, so since this is a gzip compressed data, we are going to uncompress it to extract the data of files or programs present in this compressed data. So I'm going to use star and decode it. Alright, so we successfully extracted two files from this compressed data. One is CTF, and the other one has 67B8601. So let's see their file type. So I'm going to use file CTF. Alright, so the first one here is a 64-bit Linux executable and linkable format, and the symbols are stripped, which can make binary analysis somehow difficult because the symbols, the variable names, the functions have been stripped. All right, so since we have this here, so let's check the second one here. All right, so the second one here looks like an image file. So I'm going to open the directory here to confirm that. All right, so we have it here as an image file. So we have it as well, Windows BPM image. See it over here, Windows BPM image. All right, so what we are going to do now is this. Since this is an image file and this one here is executable, how do I know this? Because of this color in Kali Linux. Executable files are given different colors than the other files present in the same directory. That's why we have others as white, and here we have it as, I think this is light green, right? To also confirm that, let's run this command here. You can see it here as what? Read write executable for both the user group and also the others. Read execute for the others. All right, so I'm going to run this CTF. Okay, so we got an error while loading shared libraries. All right, so this particular file here, this program here, is dependent on this shared library here for it to be able to run successfully. Now, since it couldn't find this library here, we got an error and the program was not able to run successfully. Okay, so what we're going to do now is we are going to see if this shared library is present on our Linux system. Let's run this and see. This command here helps to know the dependencies or the shared libraries that a program is dependent on while it is executing or before it executes. All right, so we have others here which are available on my Kali Linux. We have this available on my Kali Linux, and also we have this here available on my Kali Linux. But this one here was not found on my Kali Linux, and this is what this program needs to run successfully. So how are we going to discover this shared library here. And if we display the content of this directory here after we extracted the content from the content of this file here, which gave us CTF and 67B8601, there was no lib5ae9b7f.so library. So which means since this file here is a compressed data or a compressed file, which means within it or within these two programs here, this lib5ae9b7f.so shared library could be present either in this file here or this one over here. All right, so let's confirm that. I'm going to use SSD to display the content. First of all, let me clear this. I'm going to run this and let's display the first 10 lines. All right, so we have the content here of this CTF here. Now this is how a Linux executable and linkable format is supposed to look like. The first uh the first row here, or let me just say the first, how many bytes are these? Yeah, the first byte here has to be 0x7f, and then the second byte here has to be E. This is ASCII, this thing for E, and here we have E for L, and also here for F. So which is similar to this ELF, and we have it here as well, ELF. So this is how a Linux executable and linkable format is supposed to look like. All right, so there's nothing wrong with this file here. So let's see the second one, which we extracted by displaying the first 10 lines. All right, so there's something fishy going on here in this image file here. Remember a few seconds ago I talked about this F file here, right, which is supposed to be the starting point of every Linux executable and linkable format. But in this image file here, we have the F starting somewhere else in the file, and we have here as B, M8 and other gibberish, and so that means this program here is fishy, and this program might be hiding something, maybe perhaps our share library, which this particular file here or this program depends on. All right, so how are we going to do this now? I'm going to open another terminal here and show you something. Now in Linux we have let me use less user include f.h. All right, so this is how the Linux executable and linkable format looks like. So okay, yeah, we have it here. All right, so all the information you can find in the Linux F file is present here. This is the structure, this is the data structure for it. All right, so since we have it here, we have this e-ident here, which is where the ELF and 0x745 I talked about, this ELF and 0x7f, and in fact everything here in this line here is present in this unsigned char e-ident data. All right, so for this can look somehow to you, but I'm going to try to read the content of a Linux executable, and let's see. All right, so you can see 7f 45 4c 46, similar to this CTF here, right? 7f 45 4c 46, right? Now that's how a Linux F file is supposed to look like. All right, so one more thing here, since this image file here has an F file within it, which means perhaps our library, which this CTF depends on, is hidden inside this image file. All right, so how are we going to extract this right now? Now for we to be able to extract this, we are going to make use of the dd command to extract the data, to extract from this point here downwards. That is our F file. All right, so what are we going to do here now? If you take a look at this particular place here, the data structure for an F file, which is the executable header, this is just the executable header. We also have the program header, we have the section, and we have lastly the section header in a complete Linux F file. All right, so since this is the executable header, what we have to do right now is we are going to know the size of an executable header in Linux F files. There are 64 bit, or sorry, 64 bytes, not bits. Sorry, there are 64 bytes. All right. So since we know the length of an executable header as 64, what we need to do now, we need to copy. That means we need to copy that 64 bytes from this place downward. That is from this image file here. Understand? Okay, so I'm going to, sorry for that. I'm going to display the file again. All right, so let's do the copy. So now now how do we know where to start reading from, since this F file is starting here? All right, so what we need to do right now is we have 30 here, right? We have these 10, 20, 30, 40, 50, 60, 70, 80, 90, right? All right, so this is the row where this fi is found, this row here, right? All right, so we're going to count. This is 1 byte, 2 byte, 3 byte, and then 4 bytes. Remember, every Linux F file they start with 7F. So now we got what, 7F here. So that means we need to make use of this here. So that is 4 bytes. 1, 2, 3, 4. 4 bytes. All right. So that should be 0x34. So 0x34 in decimal is what? I'm coming. Let me my calculator. So 0x34 in hexadecimal should be, let's call this. All right, so it's 52. So we're going to skip 52, right? We're going to skip everything from here upwards and also start reading from this F here. All right, so now the count, we need to count as what, 64. Now the count is the size of the executable header of every Linux F file. All right, so we need it at 64. Then the E file, the input file we need to use here is what, 67B8601. Then the output file here, let's call this let's just name this our F header, right? All right, so we're going to use a block size of 1. That means we need it to be sequential, 1 byte at a time. All right, so let's run this. Okay, so I'm going to display this. All right, so we have this header here extracted from this image file here. All right, so now let's try to read this file. All right, so on trying to read this file, we got the magic value 7F45, which is good. That means we successfully extracted this F header from this particular side downwards. All right, so that is good. Okay, but there is something at the end here. We have error reading 1728 byte extend pass end of file for section headers, and also error too many program headers 0x7. The file is not that big. All right, so what could be the issue right now, since we have successfully extracted this particular F header from that image file? So what I'm going to do here now is remember, like I mentioned earlier, a Linux F file contains the executable header, the program header, the section, and also the section header. Now the section header is the last structure, or let's just say the last segment in a Linux F file. So for we to know the full size of this F file we are trying to extract from this image right now, we need to be able to calculate the section header, which is the last or the bottom segment in a Linux F file. All right, so what we're going to do now is this. We're going to perform some calculation here. Now we have here what as the start of what the section headers, which is 8568, right? So we're going to, and also we have here as let's see, we have here size of section headers here as 64 bytes, and also the number of section headers as what, 27. That means we have 27 64 byte section headers. So for we to find the size, or to know the size of the section header, we need to calculate 8568, which is the start of section header or the offset 8568, then plus the multiplication of 64 and 27. So for we to do that, I'm going to start up my calculator here and let me switch to standard. All right, so 64 times 27 is equals to 1728, right? All right, so 1728 was the offset of 8568 plus 8568 equals to, all right, we have it as what, 10296. So this is the full size of the Linux F file we are trying to extract from this image here as what, 10296. All right, so we are going to run dd again. So dd skip is equals to what, 52 as before, then the count, which is the size, 10296, right? And then we have 6 here, and then we have the art file. Let's call this, we're going to name this the shared library this program depends on. So I'm going to run this again so that I can be able to capture the name. So I'm going to copy this, Ctrl Shift C, then back here, and we're going to paste it here. All right, so block size of 1, and let's run it. All right, so we've successfully extracted this shared library. Now let's try to read it again to see if we discover any error. All right, so there's no error displayed again. All right, so this is what this particular file here, the CTF program depends on. All right, so we are going to set this shared library in our directory path, that is in the path where this CTF can be able to find it. So I'm going to use the library export. All right, so export, sorry, supposed to be library path is equals to, let's make this a present working directory. We can just do it this way. All right, so I'm going to run this now. Let's see. All right, so we didn't see this error message being displayed again, so which means that this particular file runs successfully. So let's see if it runs successfully by using this. All right, so we got a 1 instead of a 0. All right, so what we're going to do now is we're going to see if this particular file is maybe it wants, maybe like it needs another file or another dependency for it to run successfully, because this was not the output we're expecting. All right, so why I say so is this: whenever you run something like cat, let me just say echo John, and if I should run this, you see the value return what is 0, which means this was executed successfully. But when we run this file here, we got a 1, which means it did not execute successfully. All right, so what I'm going to do now is let's try to read strings and see. Let's check the content of this, the string content. All right, we have some sections here, .bbs, .fini, .gnu.hash. All right, so we have here is kind of like Louisiana or Dagoba where Yoda lives. No, let's see. All right, so we have some mangled C++. All right, so this is a C++ file because we have some mangled names here, which is common in C++ files done by C++ compilers, which start with a capital letter Z and other information. All right, this used in the function of overloading in C++. All right, so let's go on and see. This. All right, so we have a debug here at v equals to modulo x. All right, so this means this is expecting a command line argument to it. Then we have checking modulo s. and then we have show me the flag. We have flag is equals to modulo s. Then we have guess again. All right, so these are of interest to us. Okay, so what we are going to do now is we are going to see if this show me the flag here is the argument, is the command line argument this program is expecting from us. So what I'm going to do now is let's run it. CTF show me the flag. All right, so we got that right. Okay, now let's see if we still got 1. All right, so let me run that again. Strings CTF. Remember, we got to here checking show me the flag and OK as the strings. So when we come over here, we have checking. Yeah, we got checking, and also we have OK. Where is that? OK. Let's just not waste time on that. Okay, so since we got these, what we're going to do now is, remember I talked about mangled names or functions earlier. So let's see them out. Let's see. So we can use this nm -d, the mangle CTF. Let's see. Let's wait for the output. All right. So the mangled names we saw in that string output over here, they have been decrypted. Sorry, they have been demangled. All right. So this is of interest to us. This means this program performs encryption and decryption of strings based on what we have here. R64 decrypts and R64 init. Now this R64 is a simple cipher. It's a cipher that is known for its for its speed and simplicity. All right, so that means this particular program here performs encryption and decryption. Okay, so since we have that, let's try to see what the program coming. Let's take a look at that string again and see if we can find anything interesting. Okay, we use this and we got checking show me the flag, and then we got OK, right? Now this is where OK, which means this particular program is expecting a special input from us so that it can be able to show us the flag, because since we have it here as flag is equals to, that means this is where the flag is supposed to be. Now the modulo S here stands for string, which is used as a format specifier in C programs. So this is a C program. All right, then we have guess again. Okay, so let's perform some analysis here. Let's use ltrace. Let's try this first and see. All right, we didn't get anything special here, right? Really, the first few lines of output are just performing memory mapping and memory protection. So the things that are of interest to us are stuff that are close to the bottom here. So since we don't have anything good over there, let's try to run ltrace again by passing it show me the flag, the command line argument. All right, so now you can see we have something interesting here. We have, right, remember the printf function which we use in C program. They perform a system call, which means when it performs system call, it converts to the write, makes of this write system call. All right, so we have checking show me the flag, checking show me the flag. Then we have printf or write OK. All right, so this is not giving us what we need, because in the string I talked about, CTF, this program needs to print out the flag to us. Remember what we are doing today is what capture the flag. So this program needs to print out the flag to us, which we have here. So, and in this output here, we have nothing like flag. We just have checking show me the flag and also OK. All right. So what I'm going to do now is I'm going to let's try ltrace on this and see CTF show me the flag. All right, so we have something interesting here. We have string compare, show me the flag, show me the flag. All right, so just like I said, this program expects a command line argument from us, which is show me the flag. So it checks if it is correct. So we have this comparison here, show me the flag, then printf OK. Then we have this encryption, and we have this decryption here. All right, and then we have print get environment guess me. All right, so this just gave us a hint right now. This so let's assume this program here is expecting an environment variable from us. All right, so what we're going to do now is mm, we're going to set an environment variable with an arbitrary value, which is guess me, and try running this ltrace again. So I'm going to say, let's call this guess me is equals to, let me give them my name, John, and let's run this in the context of ltrace show me the flag. All right, so let's see. Yep. So remember, comparing this output here to the first one here, the second output here is much more. That is plenty compared to this one over here. So that means it's because when we set this environment variable, the program performed additional functions. All right. So we have this show me the flag comparison, and then we have an encryption here and also a decryption here, which means this particular program is encrypting a file and also decrypting it at runtime. And then yeah, that's all. Then we have get env here, guess me. All right, so this get env function is trying to get the value of this environment variable, which I set here as John. All right, so we now have what, let's see. Okay, we now have an assign here. We have an assign here. Okay, and I think this is assigning to a string. I think this an encryption also, so something like that. So when we get here, let's see. All right, so this is performing encryption and decryption. I think perhaps an encryption of a file, sorry, an encryption of a string at runtime, and I think it is trying to compare the value of what of the decryption of that encrypted string at runtime and comparing it to the value of guess me. All right, so okay, yeah. So my assumption is right. If you look here, we have guess me set as John, right? So so at runtime the program encrypts. Okay, yeah, it encrypts here and decrypts a string. All right, and then it gets or retrieves the value of this environment variable guess me, and I think it compares it. And when it compares it, since John here is not equal to what it is expecting, we have what print, and we have put as guess again. All right, so what I'm going to do now is let's try to get a more clearer output of ltrace by printing the instruction pointer and demangling these names here. This z, this underscore z underscore z underscore z. All right, so I'm going to do that again. Guess me is equals to John and ltrace instruction pointer demangle the name and dot slash CTF. We have here show me the flag. All right, so let's see. Now we have the instruction pointers, the value of the instruction pointers over here. All right, so now since we, just like I explained, since the comparison between this environment variable value and what the program is expecting is not equal, we have put as guess again, right? Okay, so what we're going to do now is let's try to backtrace. What I mean by backtrace, like let's try to go forward to what happened before the program printed this particular guess again. All right, so without using guess me, show me, sorry, without using ltrace, let's try running it and see. Let's see. All right, so you see checking show me the flag, right? Okay, then we have guess again. Since this John, the value of this John is not equal to what the program encrypted and decrypted, that is the string it encrypted and decrypted at runtime. It compared it to this guess me value here and it's not equal, so we got what guess again. All right, so now we need to know where this particular guess again is, which is 0x400dd7. Now let's find that out by reading the constant string section or the dot row data. So I'm going to section dot row data CTF. Let's see. All right, so we have guess again starting here, right? All right, so this is where the guess again is starting from, and this is supposed to be what is the ASCII value for G, for the letter G? Let's find out. G here is 67, right? In hexadecimal 67. All right, so let's compare it here. So since guess again is starting from this place here, so which means this is where it's starting from. This is where we have this guess again, the first letter G is starting from. So we'll now count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A, B, C, D, E, and F. So that means the starting point of that guess again is 0x4011AF. Alright, so I'm going to open another terminal here, and since you can also use readelf to read the content of the raw data. Let's try that out and see. So I'm going to raw data CTF. All right, so we have it here. The same thing. You can see it here. Same thing. Either use readelf or use objdump. So all right, so I'm going to disassemble this right now. Let me use Intel CTF. All right, so remember we have 0x4011AF, which is the starting point of this guess again, right? We are going to start from that point backward to see what happened before we got that guess again and print out. All right, so to do that successfully, we're going to look for where that string is read. That is the okay. Let me make this a little bit quicker. Let me grab 0x4011AF. Remember, that is where the guess again string starts from, right? We have it here. Okay, so I'm going to run this. Okay, we have it as 400DCD. 400DCD. All right, 400DCD. 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 So let's go there. All right, 400DCD. Yep, yeah, this is it. So we have it here. All right, so let's from this point backward. Let's go backward and see. Let's go backward. All right, so when we come here, we have okay, we have this. All right, let's see. Compare jump equals to call move. All right, so let's start from this particular place here. All right, so this looks like a loop. This looks like a loop. This looks like a loop, and all right, so we have here, right? Okay, this looks like a loop. Now, how do I know this looks like a loop? If you come over here, jump DC0, you can see this loop backward again to what? To this 400, sorry, to 400 DC0, and we have here what? 400 DC0. That means this is reading. Okay, this is moving a byte from this is an array of string or a string. Alright, so this is the base address or offset, and this is the index. Alright, so this is reading a byte from this particular location, moving it into EDS, and then testing the bytes at this EDS here, which is the lower half of EDS here. DLDL testing it, and if they are 0, which means the input that we gave to this program is 0 or null. So this is going to jump to 400 DCD. That means jump if equals to what? To 400 DCD. And where is that 400 DCD? 400 DCD is right here. All right, so this is where we get that printf guess again. That's print out guess again. So this means that it's comparing the output. It's comparing the value of the environment variable, which is the guess me, which I I use here as John is comparing the, let me open it. It's comparing this value here, John, to what it expects, and since they are not equal, we're having what, guess again. And also, even though it's not about the value of guess me, if this is null, it's still going to what, print guess again. So you see, all right. So that's what I just fished out or extracted from these code blocks. All right. So now let's go back. So if this is not equals to 0, we have compare dl byte pointer RCS. So it's still reading from this particular location here. As usual, RCS here is the base address and RAX here is the offset or the index. Sorry, the index, not the offset. All right, so it's reading this into the lower half of EDX, which is DL, and then jump if it is equals to 400 DEO. All right, to 400 DEO here. So here it is incrementing the index, which is the racks here, incrementing the index, and also comparing the index to the length of, I think, the string it is using for the comparison, or what it is reading from this particular memory location here. Is comparing if the length, if it has gotten to this length of 0x15, and then if it is not equals to 0x15, then jump to 400 DC0. So go back to what, 400 DC0. So this is a loop. All right, so what we're going to do now is let's try to dump the content of RCS, since it's the offset or the base address where this byte is being read from, into this DL. All right, so press this is a comparison, right? All right. So let's go up again and see. Okay, so you see we have, remember the value of guess me, which I use as John, that environment variable guess me as John, is the value is being moved. All right, we're moving the value from here to EDS, right? Okay, so when we move it there, we test if it is 0. So since this EDS, now this EDS contains the value of guess me environment variable, which we use here. It contains the value of this guess me environment variable here. So since it contains the value of that environment variable, which is being read byte by byte into EDX, then here we now have the comparison, which means it's comparing the value of guess me, which we gave the program, to the particular decrypted string inside this memory location. Remember, this program makes use of RCS for encryption and decryption. All right, so this is comparing our value byte by byte, that is each character by each character, that is character by character, to what it expects or what is present in this memory location. So since this is encrypted and decrypted at runtime, that was the reason we couldn't find it when we ran the strings on CTF. We couldn't find it anywhere here, and also that's the reason we couldn't find it anywhere here when we ran ltrace. We couldn't find it here. We just got this guess again. All right, so how are we going to dump the content of this memory location right now, since this is done at execution time, that is dynamically? All right, so that is where we are to make use of, I'm going to open another terminal here, GDB. So I'm going to run GDB CTF. All right, so we need to set a breakpoint at this particular location here, DC8. Yeah, 400 DC8. This is where we have this memory location which we want to dump. All right, so we're going to run this B 0x400 DC8. All right, so breakpoint at this particular place now. All right, and if you recall, we also have the program requires environment variable, which is this guess me here, and also the show me flag. All right, so we're going to set the environment variable. So let us name it set guess me is equals to let's just name this as John again. All right, and then let's run it with the command line argument, show me the flag. All right, so error while loading shared libraries. Error while loading shared libraries lib. Alright, so I forgot to set that up in this. Remember, I was opening terminal by terminal, so we need to export the ld library part is equals to the present working directory. Have it here as this. Alright, so let's run this again, and we're going to set the breakpoint at 0x400 dc8 again, and then we're going to set the environment variable guess me is equals to John, and then let's run it. Show me the flag. Alright, so we now have it at the breakpoint, right? So let's display the instructions at this particular breakpoint by dumping the content of the program counter. Alright, so we have it. Alright, so we are here. Compare RCS RAX. You can see it here. Compare RCS RAX. And also let's see if the RAX, which is the index, is okay. That is the content of the index, RAX. Alright, we have it at 0, so this is the offset. This is where it's starting from, right? Okay, so now we are about to dump the content of this RCS register here. So I'm going to run this RCS. Alright, so we have the content here. I think this should be the decimal representation of this hexadecimal value here. Alright, so since we have it here, this is a memory location, right? From what we know, this is the base address and this is the index. Alright, so what we're going to do now is we're going to use X to read the content of this memory location 6156E0. So let's do that. Alright, so this is what this program has been expecting. Crackers don't matter. Crackers don't matter. Alright, so let me open another terminal here and see. Now let's set guess me to crackers don't matter, right? Let me see. Okay, crackers don't matter. So and let's run CTF. Show me the flag. Shared libraries again. Sorry. Library path is equals to pwd. Alright, so let's run this. Alright, so now let's see if we are correct. Okay, now we got 0 instead of 1, so this means this program executed successfully. Alright, so this is the flag the program wants us to find: 84 B3 4C 12 B4 and all that. Alright, so thank you for watching, and if you know you're just joining my channel, please do well to hit the subscribe button and don't forget to turn on the notification bell so that you don't get to miss any of my videos. Thank you for watching and do have a nice day. Bye.